So we built the pipeline machine in the last video, and we traced through the execution of an example instruction. Let's look at some of the implications of the choices we've made, right? There's very little actual control logic needed here because each stage of the pipeline just does its thing. So there's very few decisions to make, right? There's a couple of multiplexers here and there, but each stage basically does its own thing over and over again. This will be true for simple pipelines, but as the pipeline gets more complicated, there'll be more control information needed to be sort of kept from one stage to the next. The other thing to keep in mind is that if you're operating on the program counter, that needs to be treated differently, right? A lot of modern architectures treat the program counter as a regular register living in the register file somewhere, and that's fine, but we have to treat it a bit differently in the context of the pipeline, especially if we are adding an offset to it to get to another instruction to execute because of a branch. Right? So the program counter is a usable, user-accessible register, but its value is going to be 2 pipeline stages behind the current instruction because we are loading instruction two instructions later when we are executing the instruction we're looking at right now. So by the time we're looking at the program counter, it's PC plus 4, right? Because every word, 32-bit word is 4 8-bit addresses. And it's PC plus 8 by the time we reach the execute phase. So the machine has to keep this in mind and very carefully make sure that we are adding the right offset to get back to the branch. Once we figure that out, it'll be the same for all instructions, but it's a thing we have to be really careful of. And the more of this kind of stuff we do, the more messy control gets. So that's fine. Let's look at the theoretical aspects then of how we represent instructions that are flowing through the pipeline. There's sort of 2 different ways to look at this: task versus time and space versus time. So the task versus time takes the instruction number, which instruction we're executing, and sort of goes downward like this. So instruction 1 is executing here, instruction 2 is executing here, right? And then across the top here, we look at what clock cycle we're in. So in clock cycle 4, for example, we're finishing up instruction 1. We're executing instruction 2, we're reading the register file for instruction 3, and we are fetching instruction 4, right? So those are the 4 things we're doing at clock cycle 1 in this format. The other way to look at it is looking at which pipeline stage compared to what time frame we're looking at. So in this case, again, in clock cycle 4, we are, again, same thing, right? We're finishing up instruction 1. We are doing the execute phase of instruction 2. We are reading the register file for instruction 3, and we are fetching instruction 4. And here the instructions are sort of lined up on this angle here. This, I think, makes it a little bit easier to see that there are basically 3 phases of any pipeline execution chunk of code. When you start the machine at the very beginning, the pipeline is empty. We will find also that the pipeline is empty in a few other circumstances when there is a requirement for a pipeline stall or something like that. We'll get to those in a minute. But when we are starting up a pipeline, the first instruction is fetched, nothing else is happening. Then the second instruction is fetched, the first instruction is read, nothing else happening. So there's this sort of gap we call startup where there are idle functional units in the pipeline. Same thing happens at the other end. If we have some reason we have to stop the pipeline, if there's some error or something and we have to flush or drain the pipeline, then there are going to be these functional units that are not used as we finish up the instructions that are in the pipeline. And so we can then sort of measure the performance of the machine based on assuming before we pipeline, how many clock cycles it would take to finish these instructions. And then after we pipeline, how many clock cycles we can take to finish these instructions. And in the ideal case, we are finishing 1 instruction per clock cycle, even though it takes us 3 instructions before we finish, or 3 clock cycles before we finish an instruction. And it takes 3 clock cycles after we start the last instruction before it gets finished, right? This is, again, this sort of trade-off between latency and throughput. Latency is how long it takes for an instruction to finish. Throughput is how many instructions we can finish in a given clock cycle. So look at some of these notes, right? We said this stuff already. At the beginning of the pipeline, most stages are idle. It takes 4 clock cycles to complete the first instruction. And at the end of the pipeline, we have to wait 4 cycles after we start the last instruction before it's done. And again, there are times when we have to do this, when we have to start the pipeline from scratch, or we have to flush out the pipeline because something has happened, right? So we have this consideration that maybe we're not actually getting as much benefit as we wanted because we have to start it and flush it. There are the times where these bits are idle. What is the actual speed up, right? There's all this extra hardware we need, all this extra logic. There's these registers between each stage. The whole thing is going to take a little longer, right, than a single cycle machine. Is it worth the added complexity, right? And the question is answered by the fact that we can have multiple things happening at the same time. Each individual instruction might take a little longer to finish, but we can do so many at a time based on how many pipeline stages that we're at. We're going to get a net improvement. So let's look at that. Part of the challenge with this comparison is we talked about a single cycle machine that can complete an instruction in a single clock cycle, right? Fetch, read, execute, write, all in a single clock cycle because really nothing is dependent on anything else. Now it's taking 4 clock cycles to finish that same machine. Is this an advantage? Well, clock cycles are not clock cycles, right? And this is the main thing to think about is pipelining doesn't just allow us to optimize the use of the hardware that we've built for our machine, it also allows us to dramatically increase the clock speed because each individual functional unit can be completed in a much shorter period of time rather than having to have register file access and ALU and memory and instruction cache all in the same clock cycle. So in a multi-cycle machine, these are the examples that we've got here. In a multi-cycle machine that is not pipelined, right? Like some of the one bus machine that we built for LC3 or the multi-bus machines that we built it in other contexts, you can optimize a little bit, right? You can keep your clock cycles short because any clock cycle is just how long a single functional unit takes to operate, take the result from the bus, do something, put the result back on the bus. And we can make instructions be different lengths, right? If something doesn't need 5 cycles, then we can make it shorter, right? So we can actually get faster instructions. The problem is we have to wait till one instruction finishes before we start the next because the ALU is used for everything. The bus is used for everything. So we cannot sort of overlap operation, okay? So fast clock cycles, but longer execution times. Then, if we compare it to the single cycle machine where we're doing everything at once, right, we can optimize a little bit, we can make things faster and more consistent, right? But the clock cycle has to be longer because we have to do register file and ALU and everything else in a single clock cycle. Pipelining really is the best of both worlds because we keep things consistent, right? And we can overlap. And that allows us to, even though we're still only completing one instruction per clock cycle, we vastly improve the performance of our machine because while we're waiting for execution to happen, we can get the next thing ready to go. So this is the main benefit to pipelining machines is that we get improvements over not just single cycle machines, but also over multi-cycle machines.